Okay, so this is my BoostPython tutorial. I gave it about I guess a month or two ago at my WattPy meetup. So this is very exciting to be able to give it to Chippy here. So I'll start with what is BoostPython, and I break it down from a pros and cons point of view. Basically, what BoostPython does is it enables you to set up a declarative or chaining style interface to bind functions in a Python extension module to a C or C++ method. And it actually enables you quite easily to write Python wrappers, as opposed to just going to those bare bones kind of roots of CPython and figuring out how to bind code. There's performance and style gains of native code with the user friendliness of a Python API when you're done binding your code. So what you get is basically Python objects and functions that call into C++ code, and everyone just thinks they're just calling a pure Python library, and in fact they are calling a native code. So what are some of the negatives here? Well, you need to carry around these binary dependencies with your Python project now, or your Python bound to C++ project. So you need a DLL or a shared object library. So if you're using Python 3.7, you need BoostPython 3.7.so, and if you're doing something numerical and you're using NumPy, then you need Boost NumPy. So with Python, how it resolves dependencies at runtime means it's difficult to use all C++ features, and especially templates, which rely on static dependency resolution. There's actually a similar lightweight header-only library out there. It's called PyBind 11. The 11 stands for the C++ 11 standard. And I actually learned about PyBind 11 after having written all the bindings in BoostPython. So I'm going to continue carrying the torch for BoostPython, even though I'd caution anyone or suggest to anyone starting out a bindings project to check out PyBind 11, because it might relieve some headaches later on. And as a final note, and I'll get to this later in the talk, packaging projects that have native dependencies can be challenging, and there's a couple of reasons for that. So how do you get BoostPython? If you're in an Anaconda or Miniconda environment, it's pretty simple. Although this package seems out of date, the last time I checked, you can do conda install py-boost, or if you want the bleeding edge stuff, you build from source. And the way that's done, you can, on a Unix-like system, you can just download the tarball, untar it, and then basically there's a two-pass kind of system for setting up BoostPython and installing it in your system. And it's, you call the bootstrapper and you have to tell it explicitly, I want the libraries for Python and NumPy, and you have to point it at your Python binary. And there's one last trick. You have to somehow either by changing the text files, and I never really got this right, or by setting an environment variable, which I did figure out how to do. You have to point it at where your include path for the pyconfig.h is. And then you call into Boost's home-built build system, which is called B2. It's short for Boost Build. And you tell it where you want to install it. That's the prefix, Boost 172 in this case. You say, I want, with Python, I want the release variant, not the debug one. I want to do shared linking and not so dynamic and not static linking. You can tell it to build with multi-threading, and you want the runtime to run on shared. And you can choose which tool chain you want. So in this case, I'm specifying GCC, and I'm saying, we're going to install as well. And stage is the other alternative. What about Windows? So it's the B2 system is meant to be cross-platform. I haven't actually delved in and tried this, but they have a bootstrap.bat, which is essentially the replacement of bootstrap.sh. And you would run that with the same arguments. And then you'd run b2.exe with, or whatever kind of executable file it is. The supported tool chain seems to be Microsoft Visual C, C++. So I've seen some GitHub threads about complaining that MinGW doesn't work, so I wouldn't recommend that. But maybe some of these other platforms like Cygwin or Windows Subsystem for Linux might work. But I'm not a huge fan of Windows. Like, I'll ship to them, but it's been a love-hate relationship for me in my career with Windows. So say you install your BoostPython libraries, you want to write your first binding. So canonically, you want to find that hello world example, and you want that to be your first implementation. So what does that look like on the C++ side? You'd pull in the BoostPython library, and you can create a struct or a class called greeter with a standard constructor, and then you have a method that says hello world with a new line, and then that's all standard boilerplate C++. But then where it gets interesting is you say, I'm going to have a Boost_Python_module called hello, and it's going to bind the class greeter. So you're passing the type into the template argument to the Python object greeter, and then you're going to say it's got the init default constructor, and you're also going to define the greet_world Python method to bind to the greeter : greet world method in C++. So forget about all the fancy build abstraction we have these days. Say you want to just straight up call the G++ compiler. I don't know why you'd ever want to do this, but because we have a single C++ file for our hello world -py file, let's just do it. So you pass in the optimization parameter to G++ -02. You tell it where the boost include files are. So -I boost installation root. You pass in where your pyconfig file is. So user include, or I guess USR stands for Universal System Resources, not user. So silly me. USR/include/Python 3.7m. You pass in which C++ file you want to build, -f PIC for position independent code. And then we tell it, hey, link to BoostPython 3.7. And then it turns out you have to pass in some linker flags. So you have to set the so name. Sorry, my cat's going nuts here. That's just COVID-19 result. But so name, hello, and you want to make it a shared library, and the output is hello.so. So if you test that out, I did this to make sure that this example actually works. You can try it at home. You can impress your wife and kids a lot, or your husband, as the case may be, life partner, whatever. Python 3.7 import hello greeter hello.greeter greet world, and then you get the result hello world. So a lot of work for hello world, but that's kind of the point of hello world, I guess. So say you wanted to expose a Python list, and you wanted to do it with a few C++ static methods. If you want to make it cross-platform, you need to explicitly tell MSVC what you want to export in your DLL and what names you want to expose, whereas like the GNU compiler tool chain will assume you want to export everything because Go open source. So basically, you have that distinction there with your class declaration, and then you say, all right, I'm going to have a public method. It returns a BoostPython list, or just a Python list, but Boost is the one who's providing the internals there. And it's you say, okay, so my coefficients for Runga of 4 are going to be a BoostPython list A, and I append all those coefficients, and then I do the same thing for the Runga of B coefficients. So this is what Sivji was joking about, is like our numerical methods for Adams, Bashforth, and Runga, these mathematicians who came up with the underpinnings of numerics. So getting to exposing lists with static methods, continuing on with that, to write the binding, you say, all right, I'm going to take my C++ class, I'm going to bind it to a Python class called lcirc4, and I'm going to define a bunch of read-only properties. So you can say, because it's a static in C++, you have to say it's an add static property, but you give the Python name followed by the address of the C++ method, and then you can provide a doc string optionally. And then if you jump into Python 3.7, you can import that module, look at the various properties and see, yes, they are what they should be. And the great thing about filling in doc strings there is you get automated auto pydocs, as the slide suggests. So you can type help on an object and you get this nice reference sheet explaining how your Python methods are bound to C++. So it's quite powerful. It does a lot for you. It's really great. So if you don't like just calling G++ directly, of course, there's make, CMake, MSVC, other things. But if you're interested in shipping your module, you'll want to consider using setup tools if you want to build a wheel or something like this. So just to show you what that looks like, you will want to import the extension class from distutils core, and then you'll be able to use the extension class to define what your extension is and what source files it has, what dependencies it has, and so on. So here you pretty much have a standard setup tools.setup clause where you define your version metadata, the contact author, the description, and so on. And then you say, like, what platform tags does this project support? So in this case, Many Linux 2010, Windows 64, Mac OS X. And then the extension class can be called to say, like, all right, there's extension modules in this project. Here's what they are. Here's what their dependencies are. Here's how to compile it. So a bit heavy in terms of, how long it is, but it's all pretty much the same arguments that you'd pass to just G++ if you had to compile it directly. So then once you've got your setup.py file written and validated, you can just build your wheel as a binary distribution, and you can also build a source tarball with sdist. So what I'd recommend for anyone who's building native extension modules to check out Audit Wheel, because it takes any like sub-dependencies of your project and bundles them in with your project. So it's kind of an interesting exercise. What it does is it takes SHA-256 hashes of any sub-dependency of your project, and then renames those shared object files to contain that hash. So what you have to do then is mangle any code binary code that references those modules, and then change the names accordingly. So there's a lot of binary mangling and crazy stuff going on, but that's for another day, I guess. So the other note, there are specific containers for building Python native extension modules for C++ that need to be used if you're going to publish to PyPI. So those are in the form of PEPs, and there's one called Many Linux 2010, which is the more recent one, and then Many Linux 1, which is the original one. And there's talk of Many Linux 2014, which is based on Ubuntu 2014. And the idea there is, well, I'm going to take a really old version of Linux that future versions of Linux are going to be dependent on, and then naturally, since things are backwards compatible, if I build on that really old version, then I'll support a whole bunch of versions of Linux moving forward. So it's kind of an interesting idea and an interesting exercise, but just take note that you never want to label your project as Many Linux or fake the metadata files, because you feel the wrath of some of these Python wizards that are out there. So here's an example of Antoine Poitrou commenting on the TensorFlow project, saying, just chiming in here, it's counterproductive to claim your wheels are Many Linux 1 compliant when they in fact aren't. This is producing annoyances for other projects in the ecosystem, the Python ecosystem, who have to deal with bug reports such as PyArrow crashes when I try to use it alongside TensorFlow. +7. And then this prompted the TensorFlow guys to pitch the specification for Mini Linux 2014. So we'll see how that goes. So I was supposed to remind you to ask your questions about 5 minutes ago, but feel free to ask me any questions. Hit me up on Twitter, or I guess GitHub doesn't have messaging, but I am at Steinmoeller on Twitter and GitHub. So thanks very much for listening. I hope you learned something.
Thanks so much, Derek. Can we give Derek a round of applause in the chat? Also, we do have some questions coming in. While we're waiting for that, it's like, what are some of the performance, like how much performance can you gain from going from Python to just like Python bindings for C?
That's a good question. It's not one that has a direct answer because it's very context dependent. I would say that quantifying the performance of Python itself is in particular a challenging proposition because Python has just-in-time compilation, and things like Numba and such are making things more native-ish, like every day. Certainly, if you find Python is slow, like you have a doubly nested loop and you're going over an array, like maybe if that's the only way of doing that, and you can't vectorize it within Python, consider writing a C++ binding into it and seeing what the performance gains are. It's very hard to like look at a piece of code and a priori say like, hey, this is slow, let's C++ify it. Like, it doesn't really work that way. You got to sort of dig and experiment yourself.
Yeah, you should always, before you do anything, always measure code. I would love somebody out there to give a talk on like C profile. That'd be fantastic if anybody's out there listening.
Yeah, that would be great. Sign me up for that one.
Yeah. We do have a question coming in. So how have you used C++ libraries within Python for either work or personal projects?
Yeah, that's a good question. So as I mentioned, I'm sort of a numerics junkie by trade. So when I finished my PhD, I said, I did enough MATLAB. Let's try to learn some C++. Let's try to make some performant things. And so my main project with the WQCG, or the Waterloo Quantitative Consulting Group, which is a not for profit I started, is a suite of numerical solvers that have Python bindings for them. So it actually started out as a C++ project. And I just said, hey, it's going to be GNU licensed. It's going to link to everything that's already out there. I'm not going to reinvent the wheel. So then things like Audit Wheel became extremely powerful for me. And I could just pin dependencies based on their SHAs and link here, there, and everywhere to things I want. Pull all those other C++ or C or Fortran or whatever it is libraries in, and just leverage them, because why reinvent the wheel, and just use it the way it's already optimized.
That is like the most Python like way of thinking. It's like we got so many other things out there. Like, let's not reinvent anything.
Yeah, exactly.
Also, we have a part 2 of that question, but they're not really related. Like, how would you recommend getting better at mathematical thinking in order to improve problem solving in an algorithmic sense?
It's an interesting question. I kind of found myself, even with a math PhD, struggling algorithmically when I came out of school. I didn't find it to be a clear-cut path. Basically, you have to sort of read about the different ways that one solves an algorithm's problem and then figure out which one suits your personality style. For me, it's example or exemplify is what you read about. So what you do is you're given a problem and you're like, oh crap, I can't solve this at all. So you just start writing down examples, like maybe for the case where there's like 3 elements in my list, I can solve this problem by doing this. And then you say, well, when there's 5, maybe I can do it this way. And then suddenly a pattern emerges. But there's other ways and there's other schools of thought. So I wouldn't get like hogtied in any one particular way of thinking, and just find what works for you, find what's out there and try your best. Yeah,
like I think the one thing that like really helped out like doing math was you learn so many different ways of attacking a problem. I was just looking on my bookshelf. There's a book I have called How to Solve It by Polya.
Okay, I've heard of that one.
Yeah. That's a very famous book. I mean, it's on my shelf, like so many other books on my shelf that I have not read. But if you're looking for a way, he's a very famous, I believe, Hungarian mathematician.
I don't know.
Yeah. So check that out.
Yeah.
So before we do let you go, thanks so much for this fantastic talk. Can we get Derek another round of applause in the chat? Do you have any takeaways or action items or words of wisdom for our community?
I do, and it's be a life learner. Never stop learning. That's my call to action. Just do it. Whatever you want to do. You think that learning comes to an end at some point in your pedagogy or your career, and the answer is no. Always look for new things to learn.
Yeah, that's fantastic advice, like especially in this field where things are going to be coming out probably forever. Like we're just going to add another examples of abstraction on top of things we already have.
Absolutely.
Awesome. Well, thanks so much, Jerry, for joining us, and look forward to hanging out again.
Yeah, let's do it again.
All right, man. Take care. Have a good night.
See ya.